Here are solutions to test number 2 for ECE 461-661 control systems. This test looks at feedback and root locus plots. Now the first problem is sketch the root locus. Given a system with 5 poles, the root locus is given. Determine the departure angle for the pole at -2 plus J2, -1 plus J1, the real axis loci, breakaway points, asymptotes, and J mega crossing. So starting out, you start with the poles and the blue lines. The real axis loci is when there's an odd number of poles to the right. So it'll be between -0.5 and -infinity. The breakaway point, there aren't any breakaway points. The asymptotes, there are 5 poles, so there's 5 asymptotes. The center mass is the average of -0.5, -1, -1, -2, -2. Gives you -1.3. So I start here and split apart 5 different ways. 180 over 5 is 36 degrees. So here's one asymptote at 36 degrees. So 5 times 36 is 180. The next one is 108 degrees. 5 times 108 is 180. Again, this is clock math. 180. 5 times 180 is 180. Kind of weird things about clock math. And the complex conjugates. So those are the asymptotes. The J mega crossing is right here. It's roughly 1.2. Or if you iterate in MATLAB, keep iterating till the angles add up to 180 degrees. It's 1.1962 J. Finally, the departure angles. What you can do is I can use MATLAB to find the departure angle for the pole at -1 plus J. I input G of S into MATLAB, pick a point, -1 plus J, epsilon to the right. So I'm going to pick a point right here, calculate the sum of the angles from the poles, and find the angle. And I prefer degrees. So all the angles of the poles add up to 126 degrees. It's got to be 180. So I'm off by 180. So I need to add 53 degrees. This is actually a pole. When you divide by a pole, divide by a complex number, you subtract. So to add 53 degrees, I actually have this be -53 degrees. So when I subtract -53, I really add 53, double negative. Puts me at 180. You can kind of see from the graph, the departure angle is negative. Let's repeat for the pole at -2 plus J2. So if S is -2 plus 2J plus 1e minus 6 plus epsilon, evaluate, find the angle, it's -100 degrees. I want the total to be 180. So I am off by, oops, try that again. 79 degrees. I want to subtract another 79. Since this is a pole, when I divide, I subtract. So if the angle is plus 79 degrees, that'll subtract 79, putting me at 180. And you can see that from here. This is actually at 79 degrees, plus rather than minus. That's my departure angle. So that's problem number 1. Problem 2. Here's the root locus, given in blue, for G of S. Find K for 60% overshoot in the step response. Now to do that, I go to the second order damping curves and find out where is 60% overshoot. It's between a damping ratio of 0.1 and 0.2. So if you say 0.15, good enough. It's actually 0.1605. Take the arc cosine. That's the angle of the pole. So what I want to do is draw the damping line at 80 degrees. One way to do that is take the tangent of 80. I get 3. Or, correction, the tangent of 80 degrees is 6.14. So when I draw the damping line, I go over 1, up 6. So there's the damping line. What I'm looking for is this point. Where does the damping line intersect the root locus plot? It intersects at 0.63 plus J3.9. What I can do then is plug that into MATLAB or your calculator. So go into MATLAB, input G of S. S is minus 0.64 plus 3.93J. Evaluate G of S at that point, and I should get a negative real number. I'm not quite negative real, saying this point is exactly on the root locus, but it's close. K is what it takes to make the gain 1. So K is not that. K is 13.47. As a check, this wasn't asked for, but you can find the closed loop system. What is GK over 1 plus GK? This is where the pole really is. It's actually at 0.6442 plus J 3.9319. If this is close to where you put it, you did it right. Where people tend to make mistakes is they forget the minus sign. If I try to put the pole at plus 6.3 or plus 0.63, it's not even close to the root locus. That shows up with the angle being off, shows up when I close the feedback loop, the pole's off. If they're close, you did it right. That's problem number 2. Problem 3 says design a compensator to give me no error per step input and put the closed loop dominant pole at minus 3 plus J2. So in that case, I start with the pole at minus 0.7, minus 3, minus 7. I want to put the closed loop pole right here at minus 3 plus J2. So to do that, I'm going to add a pole at S equals 0 that makes it type 1. Cancel this pole because it makes it too slow. Cancel this pole. So there's the form of K of S. If I add 2 poles, or add 2 zeros, I need to add 2 poles. Put a pole at minus A somewhere. Slide that around until the root locus passes through minus 3 plus J2. So that's the form of K of S. Here's G times K. Analyze what I know. I don't know K, don't know A. Analyze everything else at my design point. We get minus 172 degrees. That means the angle from A must be 7.125 degrees. Doing some trick, this side is 2 over the tangent of 7 degrees plus 3. That side's 3. Gives me 19. So A is 19. If I plug in minus 3 plus J2 into what I know now, here's GK, I get 180 degrees. That's good. That tells me the 19 was correct, but the gain's wrong. Pick K to make the gain 1, and it winds up being 26. And that's just dumb luck that the numbers came up to be such nice round numbers. It's 19. But anyway, that's what you get. And there's other solutions too. This is one solution. Finally, problem number 4 is here's K of S. Come up with an op-amp circuit to implement that. And there's a couple different solutions. If I split this up as 5 S plus 3 over S plus 10 times 5 S plus 7 over S, here's the lead compensator, here's the PI. For the lead, I've got 3 degrees of freedom, 4 degrees of freedom, 3 constraints. So pick one at random. I'll let this be 1 meg. S goes to infinity, the gain is 5. S goes to infinity, this is a short, so that's 1/5 of meg. Next, let S go to 0. The gain should be 15 over 10. That says that the total resistance is 667K. This is 200K, there's the remainder. And then the capacitor sets to 0. For these two, 1 over RC is 3. For the PI compensator, I've got 3 degrees of freedom, 2 constraints, so pick one at random. I'll let this be 1 meg. Then as S goes to infinity, the gain is 5. S goes to infinity, this is a short, that's 200K. And then for this combination, that's the 0. Here, 1 over RC is 7. Solve for C, I get 0.14 microfarads. So that is test number 2 for ECE 461.